So after the lensing for coupling improvement, we'll be seeing the fiber to fiber joints. The fiber to fiber joints is that joining two fibers of same specification. We cannot join different specifications, because if you join a single mode with a multi-mode, the purpose of transmission will not be fulfilled. So same specifications shall be used for joining, which comes under fiber to fiber joints. So after the fiber to fiber joints, we'll be seeing the fiber splicing techniques which are used for better coupling. So first we'll see some of the terminologies that we are going to use in our launching. One is the radiance or brightness, which is represented as beta, can be obtained at the source, which is at a given diode drive current. The radiance is the optical power radiated into a unit solid angle per unit emitting surface area, and it is generally specified in terms of watts per centimeter square into radians. So this is your measurement of radiance. So radiance is the amount of brightness that the diode can drive out from the LED drive or from the laser drive. Amount of brightness that it can emit. So I'll show you the figure, which is in spherical coordinates characterized by r, theta, and phi, with normal to the emitting surface being the polaris axis. So the radiance may be a function of both theta and phi, and can also vary from point to point on the emitting surface. So let us see with an example of surface emitting LEDs, surface emitting light emitting diodes, which are characterized by Lambertian output pattern. So the power delivered at an angle Q is measured relative to the normal to the emitting surface, which varies as cos Q, as the projected area of the emitting surface varies as cos Q with viewing direction. So the emission pattern for a Lambertian source will follow this following relationship, which is V of Q comma F, which is equal to B naught cos Q, where B naught is the radiance along the normal to the radiating surface, and this radiance pattern for this source is shown in the following figure. So this is the figure. So this is a spherical coordinate system that characterizes the emission of the pattern from an optical source. So where we have R is the radius. This is a Lambertian pattern. This is your emitting area center, the center point. So we divide into three, since it is being in three coordinates. So theta is the angle being formed between R and the plane, reference plane, and the phi is the angle being formed between the projected angle and the reference plane. So this is the emitting area of an LED. Okay, we are taking surface emitting LED as an example. So for a surface emitting LED, this would be a Lambertian pattern. So the radiance patterns for a Lambertian source, and the lateral output of a highly directional laser diode, which will have both sources having B naught normalized to unity. You can see that B naught will be always normalized to unity, which is cos. You can see that the optical source is present here, which is surface emitting LED. So this emits in this pattern. So this is the angle of projection of the light. You can see that at the center it is cos 180. Okay, it will propagate in zero angle, which means it in along the core of the axis. So this, if it deviates, plus 10, plus 20, plus 30, plus 40, plus 50 in this angle, and this minus 10, minus 20, minus 30, minus 40, minus 50 till cos theta. Okay. So this is a Lambertian pattern of source emitting. So the edge emitting LEDs and laser diodes have different radiances, which is V of q comma 0 degree and V of q comma 90 degree in the planes parallel and normal respectively. So if the planes are parallel, it is q comma 0 degree, and if it is normal, it is q comma 90 degree. So the radiance can be approximated by the equation 1 divided by V of theta comma phi, which is sin square phi divided by beta naught cos t naught plus cos square phi divided by beta naught cos L. So here the integers are t and L, which is written. T represents your transverse and L represents your lateral. So transverse and lateral power distribution coefficients. So if the Lambertian distribution is with a 120 degree half power beam with so L is equal to 1, so then T will be significantly larger. And especially it is used for edge emitting LEDs. So for laser diodes, L can take a value over 100. For laser diodes, L values vary over 100. Next is the power coupling calculation. So we are going to consider the case as shown in the figure with respect to a symmetric source of brightness V of AS comma WS. So AS is the area of the source and WS is the solid emission angle of the source. So with respect to that, we can find the coupled power by using the relationship P is equal to integral AR DAS integral of dr d omega b comma AS comma omega s. So which can be rewritten as with the limits 0 to x infinity 0 to 2 pi in closed brackets 0 to 2 pi theta naught 0 to x infinity beta theta comma phi sin theta d theta d phi d theta s r dr. So here the radiance B of q comma f is integrated over the solid acceptance angle of the fiber, and the q naught maximum is the maximum acceptance angle of the fiber that is related to numerical aperture. The power coupling calculation is determined by summing up the contributions from each individual emitting point source of incremental area dqs or dr, which is integrating over the emitted area. If the source radius rs is less than the fiber core radius A, then the upper integration limit Rm is equal to Rs, for which the source areas is larger than the fiber core area. Rm is equal to Ra. This is the schematic diagram of an optical source coupled to an optical fiber, where the light outside the uh, acceptance angle is always lost. So the light which is propagating away the acceptance angle will be considered as a loss. So we have an optical source chip with an active area. So this left hand side, this is your optical source chip. You have the active area. So this active area will emit light in a Lambertian pattern. So this is a Lambertian pattern it goes. And if the fiber acceptance angle is given in this way. Okay. So if the light which is being emitting when coupled with a fiber, so this is your fiber. So this is your source, optical source. This is your fiber, which consists of core and cladding. So here some part of your optical signals is being radiated outside the fiber acceptance angle. So this gets lost. So we need to couple in such a way that all the optical signals that are generated passes through the core, such that the optical sources doesn't contain much more losses. So for a Lambertson emitter, assuming a surface emitting LED, we should have RS less than A. So P is equal to 0 to gamma 3, 0 to 2 pi limits, 2 pi B naught, 0 to theta maximum, cos theta, sin theta, d theta s r dr, which can be given as phi beta naught 0 to gamma 3, 0 to 2 pi sin square theta max d theta r dr. It is given as pi b naught 0 to gamma 3, 0 to 2 pi NA, which is a numerical aperture, the whole square d theta s r dr. So for a step index fibers, the numerical aperture is independent of QS and R, so that the equation RS, so that the equation for RS less than A will become our LED at a step index will be equal to P of RS the whole square B naught numerical aperture the whole square, which is equal to twice of P RS the whole square B naught N1 square into D. This is a power coupling calculation for and step index light emitting diode structure. So which can be again extended assuming a total optical power PS emitted from the source area AS into hemisphere to PSR is given by PS is equal to AS 0 to 2 pi 0 to pi by 2 beta theta comma phi sin theta d theta d phi. So which can be again elaborated as pi r phi the whole rs sorry rs whole square 2 pi beta naught 0 to pi by 2 cos theta sin theta d theta, which can be on simplification make it pi square rs square beta naught. So this equation can be expressed in terms of PS, which is power at step index light emitting diode. The power coupling calculation is given as PS is into numerical aperture the whole square for RS less than or equal to A. So what happens for RS greater than A? So for greater than A, the radius of the light emitting area is larger than the radius of A, that is of the fiber core area. So then the equation will become for R is greater than A, power emitting at LED at a step index is A by RS the whole square PS numerical aperture the whole square. So let us see an example. Consider an LED that has a circular emitting area of radius 35 mm and the Lambertson emission pattern is 150 watt per centimeter square into steradian axial radians. So let us compare the optical powers coupled into two-step index fibers. Two-step index fibers, one of which has a core radius of 25 millimeter and another has a core radius of 50 millimeter, having both the same numerical aperture of 0.20. Okay, so we will be having will be having two core radius. One is with 25 millimeter, another with 50 millimeter. So first we will obtain for the larger core fiber, which is 35 millimeter. We will find it for 35 millimeter first. Then we will compare. So okay, the power coupling calculation for step index LED is PS NA square. So PS formula is which one which we have derived PS. In that. So PS is equal to pi square RS the whole square beta naught numerical aperture the whole square. Okay. So numerical aperture is 0.2. So substitute that 0.2 the whole square. Beta naught is given. Lambert emission pattern is beta naught. So 150 watt per centimeter square into ceridians. Then radius of the emitting area is 35 millimeter. So 35 millimeter. So convert that in centimeter and right. Then remaining pi square. So on simplifying, you will be getting 0.725 milliwatts. So kindly check whether you're getting this answer. You will get this answer. So after this manipulation is completed, we need to find the fiber end face area, which is smaller than the emitting surface area. Okay, which is 25 micrometer, which is given 25 micrometer. So the formula is A divided by RS the whole square PS NA square. So 25 micrometer divided by 35 micrometer into 0.725, which is PS into NA square. So on, so on simplifying, we'll be getting 0.37 milliwatts. It's micrometer. I'll rewrite this. Question is micrometer, not millimeter. So next is the power calculation for a surface emitting LED with graded index. So far we had seen step index. So now we need to see for graded index. So any queries till the step index power calculation? Any queries you can type in chat box. So far we had seen for LED the power coupling calculation with respect to step index fibers. So in the next slide will be, or in the next topic we'll be seeing about graded index. So any queries in the step index you can type in chat box. Some 5 to 6 minutes of time is given for asking queries. Then we'll proceed. Okay, since there are no queries, I proceed on to the next topic. No, just now after the problem, we had seen the power coupling calculation for power of an LED with step index. We are going to see power for an graded index. I think now it's audible for you. Yeah. Thank you for your feedback. So the power coupled from an surface emitting LED is being taken into consideration for graded index. So in graded index, we have RS less than A. So for this condition, we'll see. So power at LED for the graded index fiber is equal to 2 pi square V naught 0 to gamma 3 n square of R minus n to the whole square into R into dr. So which can be simplified by substituting the limits. So we get 2 pi square R square beta naught n1 square into del 1 minus 2 divided by alpha plus 2 RS by A the whole power alpha. So this pi square R square beta naught is your PS. So 2 times of PS n1 square del of 1 minus 2 divided by alpha plus 2 RS by alpha into whole power alpha is your graded index power coupling factor of an LED. So if the refractive index of the medium is different from N1, if N and N1 are different, then the power coupled into the fiber reduces by a factor R. So which is N1 minus N the whole square divided by N1 plus N the whole square. So this R is the Fresnel reflection or the reflectivity of the fiber core end phase. So this reflection coefficient is your N1 minus N divided by N1 plus 1, which relates the amplitudes of reflected and the incident wave, as we had seen in waveguides. So example, we have an example for this: a gallium arsenide optical source having a refractive index of 3.6 is coupled to a silica fiber having a refractive index of 1.48. So means that the refractive index of the optical source, which is your LED, is 3.6. It is N1, and it is coupled to a silica fiber, so which is the optical fiber having refractive index 1.48. So which is N, which is 1.48. So if the end and the source are in close physical contact, the Fresnel reflection is R is equal to N1 minus N divided by N1 plus N the whole square with respect to our formula. So substitute N1, the refractive index of the optical source, which is 3.6, minus the refractive index of the fiber, which is 1.48. So 3.6 minus 1.48 divided by 3.6 plus 1.48 the whole square, which is 0.174, is the reflection for this problem. This problem. So in this problem, the value of R corresponds to a reflection of 17.4% of the emitted optical power back into the source. So the power coupled is equal to 1 minus R into P emitted, power emitted. So the power loss in decibels can be found out from the formula minus 10 log of power coupled divided by power emitted. So power coupled by power emitted is power coupled formula 1 minus R. into P emitted divided by P emitted. So we get minus 10 log of 1 minus R. So the answer will be minus 10 log of 1 minus R is we have 0.174. So we get 0.826. So minus 10 log of 0.826, which is equal to 0.83 dB. So this is the loss for this problem, which is having a refractive index of 3.6 optical source and at silica fiber having 1.48. Okay. So this is for a graded index. So next topic is power launching versus wavelength. So the number of modes that can propagate. The number of modes that propagate in a graded index fiber of the core size A and index profile alpha is given by m is equal to alpha divided by alpha plus 2 into 2 pi a n1 divided by lambda the whole square into del. So there would be twice as many modes propagation in a given fiber at 900 nanometer than 1300 nanometer. The modes of propagation. The radiated power per mode will be PS by m from a source at a particular wavelength and is given by the radiance multiplied by the square of the nominal source wavelength. So it is PS by m is equal to V naught divided by lambda square. So twice as much power is launched into a given mode at 1300 nanometer than a 900 nanometer. So there are two identically sized sources operating at different wavelengths, but they have identical radiance or identical brightness that will launch equal amounts of power into the same fiber. Next is numerical aperture. As shown in the figure, there is power loss in terms of fiber. So at the input end of the fiber, the light acceptance is described in terms of launch numerical aperture, which is NA-IN. The light emitting area of the LED is less than the cross-sectional area of the fiber core. Then power coupled into the fiber is given by NA is equal to NA-IN. The light emitting area of the LED will be lesser than as compared to the cross-sectional area of the core fiber. So then power will be coupled into the fiber. So this is being represented by launch numerical aperture NA-IN. So in long fiber lengths, after the launched modes have come to equilibrium, which is often taken to occur at 50 meters, every 50 meters, then the effect of equilibrium numerical aperture becomes apparent. So this can be found out by the optical power in fiber scales. So where P50 is the power expected in the fiber at 50-meter point based on the NA in. So the equilibrium numerical aperture power will be PQ is equal to P50 power at 50-meter into NA numerical aperture at equilibrium divided by numerical aperture at launch, the whole square. So this is the equilibrium power manipulation. So numerical aperture versus the fiber length is taken into consideration. You can see that the numerical aperture at launch is at 0.34. So as the fiber length increases, the numerical aperture moves to numerical equilibrium, so around 0.22 as a function of fiber wavelength. So next topic is lensing schemes for improving coupling. So lensing schemes are being given for improving the coupling parameter. So the possible lensing schemes is shown in figure. I'll show you that. So such that the efficiency is increased at couplers. So a round end fiber, you can see a round end fiber, a small glass sphere in contact with both fiber and source. Then a large spherical lens which is used to image the source on the core area of the end fiber. Large spherical lens, you can see. Then a cylindrical lens generally formed from a short section of fiber. Cylindrical lens. Then a system consisting of spherical surfaced LED and a spherical ended fiber. Spherical ended fiber. Spherical surfaced and the spherical ended fiber. In a tap ended fiber. A tap ended fiber. So these are the 6 different schemes that are used for improving the coupling factor. The first diagram at the top is your left hand side. Is a rounded fiber. Have the LED or the optical source. The active area is this. So the fiber is round ended. You can see that the fiber is round ended. Core and cladding. Second one is the small glass sphere. You have see that this is your fiber. This is your non-imaging microscope. The LED is present in active area. We have a small glass sphere in between the optical fiber and the LED optical source. So this is your non-imaging microsphere. And next is your imaging sphere, where a large spherical lens is used to image the source. You can see that we have the optical source LED. Here is the active area. And we have an imaging sphere which is larger, which is focused towards the optical fiber. So next is the cylindrical lens. So cylindrical lens is replacing your image. Is replacing your sphere. Cylindrical lens. Then a spherical surfaced LED and spherical ended fiber. So a spherical surfaced LED as the optical source, and then surfaced spherical ended fiber has been connected. So then a taper ended fiber. So these are the lensing schemes that are used to improve the optical source to fiber coupling efficiencies.